we did categorical data. We had proportions, success, fail. That's what we were looking at mostly. In Unit 7, we did quantitative data. We had means. We were going in and calculating averages. Now for Unit 8, we are kind of coming back and we are doing categorical data again. And with the categorical data, oops, my pen, sad. Real quick, 1 second. With this categorical data, we are asking a different question than we did when we had regular proportions. Yeah, we are going in and we are asking 3 different kinds of questions. So for AP Bio, if you took AP Bio, you may remember a chi-squared test. I can't remember which of the 3 that you do, but there are 3 of them. We are going to spend 1 lesson on each type of hypothesis testing. So we'll do 8.1, 8.2 before you guys leave for spring break, and then we'll do 8.3 when you come back, and then we will test. So first things first, a goodness of fit test. When we're going in and when we're doing a goodness of fit test, you are trying to see, does the observed frequency distribution fit to some claim distribution? So the kind of change that's going to happen when you guys were doing a regular hypothesis test for Unit 6, you had things like HO, mu is equal to 5, or no, let's do P. Let's make it P because we're doing proportions. HOP is equal to 0.5 or HAP is not equal to 0.5. So we were basically comparing one proportion, one population to one specific claim. Whenever we're going in and we're doing goodness of fit, we're trying to see if multiple categories fit. So it's not just, are the color of red M&Ms present in the bag with a certain frequency? It's, are the red, orange, yellow, blue, green M&Ms present with a certain frequency? So you're checking all of them across the board. So an example of how this could kind of look, when it comes to a fair die, if I have 6 sides to a die, if I think that an equal expected count should occur, another word that they use for this is uniform. If I am expecting it to occur with equal frequency and I am doing this 60 times, I would expect to see each face 10 times. Because if it's an equal distribution, I would expect to see 1, 2, 3, 4, 5, 6, the same exact amount of times. Now, for expected counts, if you had to calculate this over a larger number or a different group, you can always just take your total sample size and divide it by how many categories you have. So we have 6 because it's a 6-sided die, and I had 60 trials, so that's where I got my number 10 from. But you can apply this in any situation where they are saying it is an equal distribution. Now, it's not always an equal distribution. I don't want you to think that every single question you encounter is trying to test, are all of the categories equal to each other? Sometimes they give you an expected percentage for certain categories. So in this case, they say the die is loaded and the number 1 is going to turn up 50% of the time. So that means the probability is 0.5. And then they say an unfair, the other 5 outcomes occur 10% of the time. So 10, 10, 10, 10, 10. And remember, for probabilities, they always have to total up to 1, because sometimes in that last category, they'll say the rest of them are 6, and you have to add everything else up and subtract it from 1 to figure out what that percentage is. Now, for the expected counts, if I have a trial of 60, all I have to do is multiply that by 0.5, and that is going to give me my 30. So if I'm expecting to see 1/2 of the time and I'm running 60 trials, I should see it 30. And then I kind of do the same thing. 60 times 0.1 is going to give me 6. And then that tells me, since the rest of them are all 0.10, how many I'm expecting to see. So the reason why we're doing this, whenever we calculate chi-squared, we are going to go in and see how far off are the observed values from what you should expect to see given a certain claim. So you have to know what the expected values are in order to say this is how far apart they are. Now, we found the expected counts. one of the things that you also will kind of deal with in the question is observed counts. And a lot of the time, this is going to be given to you. Sometimes they give it to you as a percentage, and you have to take the sample size and multiply it by that percentage, kind of like what we just did. But sometimes they just say, we saw this many people, which you'll see in our example today. We run a simulation of rolling a fair die 60 times. And one of the things that I like to kind of point out is you're not going to expect each outcome to be observed exactly 10 times. So we have something called sampling variability. Every time you collect a sample, you are going in and you are potentially getting a completely different sample every single time. And you should if it's completely random. Now, because of that, there are going to be some differences that are not exactly what we would expect to see from an equal distribution. So looking at our observed counts, whenever you have values that are pretty close to what you're expecting. So if I look at this, I have like a 10 and an 8, I have a 10 and a 10. Those are pretty close. They're not going to add very much. Like if I found the difference between the two, the difference in this case is 2. Difference in this case is 2. But then when I look at something like 10 and 16 and 10 and 4, I'm getting a difference of 6 and a difference of 6. Now, I did not add plus or minus in there just because we'll talk about what the formula is going to do in just a second. But those pairings that have a larger difference, they're going to be the reason why your test statistic gets bigger and eventually your p-value gets smaller and you're more likely to reject the null. So if you have a bunch of values that are pretty spot on to what they're supposed to be, you're most likely going to fail to reject. But if you have things where there are noticeable differences between the two values of observed and expected, you're most likely going to reject because you're going to say that my data does not fit what I am expecting to see. So that's kind of the test that we're doing for here. Basically, are the differences between actual observed counts and expected counts significant? One little thing here, and this is mostly for the calculator, observed counts must be whole numbers. So this is kind of a note because you will encounter problems where you are doing percentages times sample size, and it's going to give you a decimal, and you're going to put that decimal into your calculator, and when we run the test, it's going to say error. The reason being, observed counts have to be whole numbers. You don't have to have expected counts as whole numbers because they're kind of working under the idea that it could potentially be something where you have to kind of go in and change it. Now, one thing here, round like normal. Okay, now for measuring the difference, the chi-squared calculation. This is something that is on your formula chart. It's kind of a fancy looking X. It is not something you have to take the square root of. It is just chi-squared. It is a summation. So this here means you're going to take a sum of the observed minus expected squared all over expected. And I will scroll up. With the observed minus expected, you are going to take the counts that you see and find the difference between the two. Now, the reason why it is squared is one of those reasons why I talked about I didn't do a positive or negative for the difference. That's mostly because they don't want to have negative values within their test statistic. So they are going in and they are squaring each value, kind of like what your least squares regression line does. Let's see. It should be informative. You don't have to write on this paper. Okay, now to talk about what the chi-squared distribution actually is. So with the chi-squared, it's kind of a completely different thing than what we're doing, but it functions almost exactly the same way. It is no longer going to be a normal distribution. So the checks that we would normally do for a normal distribution, like n times p is greater than 10 or central limit theorem, they no longer exist. They are not what we are doing. With the chi-squared, they are going to have a right-skewed distribution. Now, the reason why they are all going to be right-skewed, if I am taking every single difference and I am squaring it, I should only be getting positive numbers. And so because I'm only getting positive differences, that is going to cause my chi-squared value to be positive and not negative. And so what you'll notice as you're starting to see and you work through some of these problems and you get test statistics, you're never, ever, ever going to get a negative. So if you get a multiple choice question and they're like, what's the test statistic for chi-squared? And you have negative answers, immediately cross them out because they are not what you want. You only want positive values for chi-squared. Whenever we go in, we have a degree of freedom because this is going to be a family of distributions, not just one single distribution like our normal Z distribution. The way we calculate degree of freedom is going to be your number of categories minus 1. So in our example for the dice, if I had 6 sides, that's 6 categories that I could potentially sort my data into. Therefore, I am going to have a degree of freedom of 5 because I take away 1. As your degree of freedom gets larger, meaning your categories gets larger, you do start to see it become more and more normal, like comparing our degree of freedom of 4 to degree of freedom of 8. But you're not going to have a ton of categories, especially for something where you are doing this in your calculator. You are still entering in data. And remember, most of the time, ideally, you're not going to have to enter in a ton of data on the AP exam. So most likely like 6 categories is probably the max that you see, but it can kind of fluctuate between like 6 to 10 and things like that. So how this actually works. If and these are observed and expected, if they are close to each other. So think back to my table of observed data. I should be getting 10, I got 10, or 10 and 8. If they're really close together, the differences are not going to be very big. So if the differences are small, and I'm going to kind of make a note here, if the differences are small, that is going to lead to a small chi-squared value. And remember, chi-squareds are only positive. So that means when I start this on the left-hand side, I'm starting at 0, and I'm going all the way up to positive infinity. So if I pick a chi-squared that's small, and I draw kind of where it would normally be, every test that you do for chi-squared is shading to the right. And so when I have a small chi-squared value, what you'll notice is I'm going to have a large shaded area, meaning I'm going to have a large p-value. So again, kind of what we were talking about just a second ago, where I said if there's not a big difference between the two, that is eventually going to cause you to fail to reject the null because your p-value is really, really big. If I have observed and expected and they're really far apart, so say the 10 and the 16, and I go in and I calculate that difference is going to be a lot bigger, which is going to lead to that large chi-squared value because it's a summation. All of the differences are getting added together. So it's going to lead to a large chi-squared value, which means, again, starting at 0 on the left-hand side, it's probably somewhere more on the right-hand side. And if I shade everything to the right of that, it is going to be a lot smaller, meaning I'm going to be more likely to reject the null. So the big thing to kind of recognize here is the smaller your chi-squared value, the more likely you are to fail to reject. The bigger your chi-squared value, you're more likely to reject. Now, this is something you can still go through. We're going to run the tests. We're going to get p-values. There is no like magic. If chi-squared is bigger than 10, you're going to reject. It kind of depends on your degree of freedom and things like that. But the big idea is we're no longer kind of in that frame of mind where if it's bigger than 3, it's probably pretty close to 0, because you're going to get chi-squared values that are like 20 and 30 and 100, and you still may potentially go in and fail to reject. So just keep that in mind. A little bit of the mindset that we had for Z's and T's is changing, but the process itself of like, how do I do a hypothesis test is exactly the same. Now, the one big change is you are no longer no defining parameter. A lot of the time, what we're going to do is we are going to write our hypotheses in words. The only one that I generally recommend writing in symbols is the goodness of fit test, but that does require defining your parameter, and we're trying to avoid doing that, but I'm going to show you how it could look. The null hypothesis should state a claim about the distribution of a single categorical variable in the population of interest. And I say that the null is the dull. So whatever they say, so it's going to be their claim. So if they say that they're expecting an equal distribution, it's equal across the board for the null. If they're expecting to see red 20% of the time, green 30% of the time, all of those things is what we put into the null. So in words, I'm going to say something like the proportion, and this is going to be our fair die example. Proportion of dice outcomes, changed color midway, is equally distributed. You can also say that it's uniform. I need to move this because I'm going to keep pressing it. Equally distributed. Sorry for my people who that one bit of green is going to drive you crazy. My bee. Okay. For symbols, you do have to define the parameter you're going to use. So I'm going to say proportion of dice outcomes. And then what you have to do, and the reason why people don't tend to like this one, is you do have to list what you're expecting to see. So we could say P1 is equal to 1 over 6, P2 is equal to 1 over 6, P3, and then you would do the same thing for all of the categories, which is acceptable, but sometimes it is a little bit more writing than what you would do if you just wrote out, like, we're expecting them to be equal. But that kind of covers the symbol side of things. The alternative is always kind of the same, at least one, because it doesn't have to be that all of them are different. It just has to be that one is different. So at least one of the claimed proportions is different. And you can kind of use some of the phrasing in their word where you're going to go in and you're going to pick, like, they're going to say certain percentages. You can say, like, I use M&Ms because it's one of the biggest common examples. The proportion of M&M color distribution matches the claim made by Mars. And then that could be enough for your null. Now, for the conditions, there are 3 of them. And 2 of them are identical to what you've been doing. Random, independent. If anything, if all else fails on a hypothesis test and you're like, I do not remember even what test I'm supposed to do for this, put on your paper that you checked for randomness and independence, because you may kind of squeeze out 1 point of those condition checks on your FRQ, even if you don't know anything else to do on the FRQ. The last check is different because remember, anytime we're checking for shape, that is usually the one that's going to change. All expected counts have to be at least 5. So yes, you do have to calculate expected counts for each question. Now, I usually go in and say all expected counts greater than or equal to 5 whenever I'm checking this. It does not require that you have to have a statement saying the sampling distribution of, and it would be chi-squared essentially, is skewed to the right. Like when we're going in and checking normal, that is something you do have to write. This one, all they require on the AP exam is that you have stated that all expected counts are bigger than 5. So whenever we write this, that's all I'm gonna say, and then I'm gonna move on. Now, before we go on, we're just gonna do one last summary of what we've kind of talked about. You have a null, and that is the claim of the whatever they're talking about, the entity that is saying that these proportions are true. That is always the null. The alternative is always that at least one of them is incorrect or different. Then you have your calculation for chi-squared. This is, again, because vocab is important, this is your test statistic. So if you have questions that are like, what is the test statistic? That is your chi-squared value. And then you go in, you take the test statistic, you use it to calculate a p-value, and the way we do that is with chi-squared CDF, and that is in second VARS 8. Now, most of you are going to kind of lean more towards using the calculator test, which is completely fine. I would always give you the reminder of don't forget about how to calculate p-value by hand, because there are questions where they'll ask you, this is the chi-squared value, what is the p-value? And you can't just take a chi-squared value and put it into a test function in your calculator. It's not gonna give you what you need. You have to remember that you can still do this by hand with the chi-squared CDF. Another reminder here, all of the tests that you do for chi-squared, does not matter which three, because there's 3 of them, this is one today, does not matter which one you're doing. It is always going to be chi-squared is your lower and infinity is your upper. You are always going to be shading to the right, no matter what. So you don't even have to make the decision within chi-squared of like, should I put negative infinity? Should I do this? It is always chi-squared to positive infinity. So whatever test statistic you get, that is your lower bound every single time. There's no other changing of directions because we're not doing less than, greater than, or not equal to. We're just doing, does it fit or does it not fit? That is our null and alternative. Okay, let's go to an example. There are some warnings. Make sure that you go in and you are double checking that this is counts. This does have to be categorical data. It is not technically a condition. I know in Math Lab, I believe one of the things that they're gonna have you mark is that you double checked that it was categorical and it was counts, but that is not something you necessarily have to have as a condition for like inference. It's just like, yes, you should be checking that before you start doing this test. And when you're checking the large counts condition, make sure that you're using expected counts, not observed. So that is gonna be the one that we're double checking is bigger than 5. Okay, let's do an example. A geneticist is studying the gene pattern of eye color in a group of white mice. He observed a random sample. He found 110 had red, 57 had brown, 32 had pink, and 13 had blue. And so sometimes they'll give you the sample size. If they don't give you the sample size, you can just take all of your observed values and you can add them up. So my sample size ended up being 212 when I took all those values and added them together. His model suggests that the distribution of eye color should occur in a 9:3:1 ratio. Is there evidence that the geneticist model is not accurate? Use a 5% level of significance. So I'm gonna go in, I'm gonna write out my null. The null is what they claim is true. So I'm going to say proportion of white mice eye color occurs in 9:3:3:1 ratio. And it doesn't always have to be like you listed that it's going to be brown is 9, red is 3. It just some kind of summary sentence explaining what you're trying to find. And then the alternative, at least one claim proportion is different. Random and independent, you should be pretty comfortable with. I'm going to say random sample of 212 white mice. And I'm going to say 212 is less than 0.10 of all white mice, which is safe to assume. Now, to be able to calculate the expected values, because we need to make sure all of the expected values are bigger than 5. How a ratio works, kind of back to way back, probably like 4th grade math, maybe. 9:3:3:1. If I add all those things together, I'm going to get 16. And so this is basically saying 9/16, 3/16, 3/16, 1/16. But we do not write the denominators normally in ratios. We just write the numerators. So that's why they write it as 9:3:3:1. So then I'm going to go in. Fun facts with Miss Martinez. I'm going to go in and I'm going to take my different eye colors. And usually if they don't tell you what order they're in, the order that they write them in is the expected ratio, because that sometimes is important. I'm going to go in and I'm going to say red, brown, pink, blue, and I will sometimes I make a table and I'll just draw it out and fill in what I need, because you do have to have all of them listed. You cannot just make the statement of they are all bigger than 5. Now, you don't necessarily have to show the work for how you get them, but I am going to kind of walk you through where it's coming from. For red, I'm going to take 212 and I'm going to multiply it by 9/16, and I'm going to kind of repeat the process and just change the ratio as I kind of move along.
So to get the denominator, you add up all the numbers in the ratio? Okay.
So like a 3-to-1 ratio would be 3/4, 1/4.
Okay.
And then 212, 1/16. Now, you don't have to have what I have here in black. That is just for us to kind of know where these numbers are coming from. You can go straight to your calculator and plug this in, and you can just write out the numbers. So you don't have to actually show the work for it on the AP exam. 39.75. And it is okay in these cases to get decimals, because this is just expected counts. For observed counts, like what they gave us in the question of what they did see, we have to kind of match and make sure that those are whole numbers. If it is something that did get like come from a percentage and you had a decimal, round it like normal for observed. And then we just say something that says all expected counts greater than or equal to 5. And this is another one where I wouldn't say if one of them failed, don't continue on with the test if it was an FRQ. All I would put in the conclusion was, however, the expected count for pink mice or pink-eyed mice was not greater than 5, so this may be inaccurate. Okay. For my people, and most of you are my people who know that they are going to use the calculator, you do have to name the test. And that is a requirement for must do for calc. exclamation mark, exclamation mark, exclamation mark. Because you are going to get very little from the calculator. You're literally going to write the test statistic down, the p-value down, and the degree of freedom. This kind of eliminates you having to do anything by hand. I am going to show you how this works by hand, but you don't necessarily have to do that if you're going the calculator route. So the first thing I'm going to do is the formula is observed minus expected squared all over expected. So I'm going to go ahead and I'm going to fill in my expected values. I saw 110, 57, 32, and 13. And then matching them up with what we calculated in the table, 119.25, 119.25, 39.75, 39.75. And so you can see how doing chi-squared can eventually be something that takes a lot of time if you are doing it by hand, because not only do you have to set this up and calculate the fractions that are going to have to then go into your calculator, but then you're going to have to type everything in and make sure that you didn't make a mistake and then get your test statistic. So my test statistic is going to be, when I plug all of this into my calculator, 9.7191. Now, the reason why I show you this, there will sometimes be questions where they ask you to calculate a component of chi-squared. And a component of chi-squared is just the fraction used for any of the categories. So each fraction itself is a component. So they'll tell you, calculate the chi-squared component for red-eyed mice. And that would be, you go to the red observed and the red expected, and you fill in this formula. Sometimes they will ask you which component contributes to chi-squared the most or the least. And whenever you get that question, you're basically just looking at which ones have the greatest difference and the least difference. So like this one at the top for the 57 minus 39.75, that's the biggest difference between what we observed and what we expected. So this is going to contribute the most, because it's going to have a larger number that is going to be squared and then eventually added to everything else. And then the ones that are really close together, like the 13 and the 13.25, they are going to contribute the least. So the most is going to be the one that has the biggest difference. The least is going to be the one that has the smallest difference. And then we calculate our p-value. So p-value is going to be in chi-squared CDF, and it's going to ask you three things, and I'll open up my calculator in 1 second. Lower, upper, degree of freedom. The lower bound, no matter what, any chi-squared test that you do, it is going to be the test statistic. So that 9.7191. Upper is going to be positive infinity. And your degree of freedom is your number of categories minus 1. So we had four different eye colors that they could have. So my degree of freedom is going to be 3. And that is going from 4 eye colors minus 1.
And you said your chi-squared value can never be
Negative. Do not want it to be negative.
Can it be like 0 or like?
It could be 0. 0 would be that there was no difference between all of your values. So you were expecting to see 10, 10, 10, 10, and you saw 10, 10, 10, 10. Because that would be no differences between what was observed and what was expected. So 0 is possible, but probably not going to happen. Okay, in our calculator, just to kind of walk through this really quickly, we have second VARs, and it's down at option number 8. Do not pick chi-squared CDF. It is chi-squared. Do not pick PDF. It is chi-squared CDF. Oh, no. Let's see. Is it going to do it now? It doesn't look like that. There we go. Let's see. Let's do this. Not now. Well, maybe it doesn't want me to show you. How sad. Which is so funny because that does not show on my screen. So I don't even know where to like press to get rid of it. Okay, well, let's see. It does not want me to do it today. It's fine. We're going to go to second bars, number 8. In your lower bound, you're going to put 9.7191, and then in your upper, you're going to put 1E99, degree of freedom of 3, and then it should give you your p-value. If you hit enter, and it should be a p-value of 0.0211. Okay, now before, and I'm going to try to switch this to see if it'll play nice with me. Before we go in, and it's not going to play nice. Let's do this. Let's close it and then see.
Rate it 0 stars.
0 stars. I pay for it too, which is sad.
Really?
I do. There we go. It's like to not have ads.
Oh.
That's not like I'm paid millions of dollars. It's like $3. So the way that we do this in our calculator is you're going to go to stat edit. And you're going to have to put your observed values in L1 and your expected values in L2. You will have to enter your data into your list. So all of the observed that we have, the 110, the 57, the 32, the 13, that's all going to go into column 1. And then all of the expecteds we calculated will go into column 2. Within, just a little note, within the expected column, you can do math. So you could go in and say 212 times 9 over 16, and you can just calculate it directly into the list versus like calculating it separately, writing it down, copying it over. You can just have it in the list on its own, and then you don't have to do like an extra step. Once your data is in your calculator, you're going to go to stat tests, and this is the only chi-square test that has its own like thing. So it should be the chi-square GOF test. I know you're going to want to write GOF on your paper. College Board wants you to write goodness of fit, so write goodness of fit out. With the goodness of fit test, the chi-square test is for the other two that you have not seen, we will not learn today. Within the goodness of fit, it's going to say, are you observed in L1? Are you expected in L2? What is your degree of freedom? We said degree of freedom was 3 because we had 4 categories minus 1, and then you're just going to go all the way down to calculate. And you should get something where our chi-squared is pretty spot on and our p-value is. Now, the only thing I am going to tell you that you have to write down is the chi-squared, the p, and the degree of freedom. This last one, if you have it on your calculator, this is actually calculating the components for each category. So like that 0.717 is for the red-eyed mice. The 7.48 is for the brown. And what you'll notice is kind of what I talked about. The one that contributes the most is the one with the biggest difference. That brown-eyed has a 7 versus the blue-eyed, which it was really, really close, only has 0.004. So it contributed the least. So that thing is just calculating the individual fractions. Don't have to write that down. I would not suggest that you write it down, but that is what's going to come from your calculator. So then we're going to go in and we are going to interpret. Since the p-value of 0.0211 is less than alpha equals 0.05, we are going to reject the null. There is convincing evidence that, and then this is where we kind of repeat either the question, if it's well worded, or if it doesn't have enough detail, give it some detail. I'm going to say the color of white mice eyes does not match. A 9:3:1 ratio. Okay. You guys will have a math lab today. We are not